This is Scott from fairlynerdy.com, and this video goes over is it supposed to be an intuitive guide to Bayes theorem to help you understand Bayes theorem. So the example we're going to be showing is Bayes theorem applied to disease testing, in this case cancer testing. And here's the problem. So let's say that you are just testing some random patient, a generic patient, for cancer, and 1% of the population has this cancer. And then you have a test which will return a true positive. So will return a positive if they actually do have cancer, 99% of the time, and it will return a true negative, 95% of the time. So 1% of the time it will return a false negative, and 5% of the time it will return a false positive. So you do the test. You take your random patient and you do the test and you get back a positive result. What are the odds that this patient actually has cancer? So without applying Bayes' theorem, just intuitively, some people might assume that the odds are really high. You might think, hey, this test is 95%, 99% reliable. It's going to return a positive 99% of the time, and then true negative 95% of the time. It should be really high chances that this patient has cancer. Bayes' theorem, we're going to apply Bayes' theorem and show that that's not the case. So a lot of examples will start with this is the equation for Bayes' theorem, and a lot of examples will start with this. But I don't want to go into this equation itself because it's not really that intuitive. It does make sense if you understand Bayes' theorem, but it's not really that good for getting you to the point where you understand Bayes' theorem. So instead, what we want to think about, we want to walk through these steps for solving Bayes' theorem, and really just think of it as probabilities that we're going to normalize. So the steps are we just need to determine what the possibilities are and what events we're observing. Estimate our initial probabilities. For each initial probability, calculate the odds of getting that observation. Multiply the two together, and then normalize the results. So I've done that in Excel. It's fairly in Excel is fairly nice to make a table, or this kind of table actually works fairly well for Bayes' theorem. So to start with, we need determine the desired probability. Determine the desired possibilities and what is being observed. So the possibilities that we have are either the patient does have cancer or they do not have cancer. So there's only two possibilities. And what we're observing is tests, results back from the test. So we're going to put the chance that a column for they have cancer and a column from that they do not have cancer. And we're going to get a row back for each test that we do. So the first test comes back and we say we have a positive result. I'm sorry. The first thing we need to do is estimate the initial probability. So the initial probability in this case, since we just have a random patient, we think that the initial probability is just going to match the probability of the population in general. We know that 1% of the population has cancer, so we're going to think that this patient initially has a 1% chance of having cancer. So if we don't do the test, if they don't even come in for the test, we'd guess that they have a 1% chance of having cancer, which means they have 99% chance of not having cancer. The second step is to get the probability that they would get a positive result if they either have cancer or do not have cancer. So if they have cancer, the probability that they're going to get a true positive result is 99%. This test will return 99% positive. Will return positive 99% of the time if they have cancer. That's a true positive result. If they don't have cancer, the test will return positive 5% of the time. The true negative chances are 95%. So that means the false positive chances, when it will return positive if they don't have cancer is 5%. That's 1 minus 95%. So what are the chances that this patient has cancer and gets a positive result? That would be the initial probability that they have cancer of 1%, and then the chance of getting a positive result if they have cancer of 99%. So the chance of having cancer and getting a positive result are 0.0099%. The chance of not having cancer and still getting a positive result is a chance of not having cancer, and then the chance that this test will come back positive even though they don't have cancer. And this is a 0.0495% chance. So the next step, that's step 4. The next thing we have to do is normalize the results. So when we normalize the results, we see that the chance that they actually have cancer getting one positive test is only 16.7%. The chance that they don't have cancer, giving this one positive test, they still have an 83% chance of not having cancer. And that's surprising. That's fairly surprising if you didn't use Bayes' theorem, because you have this 99% accurate test, but you still have an 83% chance to not have cancer. So what's going on? Why doesn't that match our intuition? Well, it doesn't match our intuition because most of our intuition ignores the initial probability. Our intuition is based only on these numbers, for the most part. We tend to ignore the initial probability unless we really give it a lot of thought. So the initial probability has a very low chance of having cancer. So this low number, multiplied by even a high percentage here, is still a fairly small number. And this high percentage here multiplied by a low percentage, in this case, is still, a higher number. Graphically, this is what it looks like. Before the test, the chances that they have cancer are 1%. That's this little blue triangle. And chances that they don't have cancer, 99%. When they come in for the test, now we have 4 possibilities. They either have cancer and test positive. They either have cancer and test negative, no cancer and test positive, or no cancer and test negative. The sum of these two no cancer circles, the purple and the green, is still 99%. That's the same as this red. And the blue triangle and the little red sliver that's not visible because it's so small is 1%. So this blue sliver here, the chance that they have cancer and test positive, almost the same size as this blue sliver here. But this green sliver, which is 5% of the 99% chance that they don't have cancer, is still larger than the blue slice. So when we actually get our test back that they have cancer, we need to only keep the slices that say they have cancer. So that would be this blue and green. And so when we remove this purple slice, this purple sliver, and the red one that's not visible because it's too small, we would renormalize, and we get, still a large chance that they don't have cancer. Still an 83% chance that they don't have cancer, even though we have a positive result. We can do more tests. If we want to do more tests, we can repeat these steps for new observations. So in the second test, we don't use this initial probability anymore. We use the probability after one test. So the second test, we might test positive again. So in this case, we multiply the 16.7% chance by 99%, and the no cancer rate of 20%, the no cancer rate of 83% by a 5% probability. When we normalize again, we now have about an 80% chance of having cancer. So the more positive results we're getting, the higher the chance that this actually has cancer. If we then do a third test and get a negative result, our probability goes down again, because now we multiply this 80% chance by a 1% chance that they have cancer but get a negative. So this would be our false negative rate. So 80% times 1% here. And we multiply this 20% chance by our 95% true negative rate. And when we normalize, we get a 4% chance that they have cancer after these 2 positive and 1 negative tests. All right, so that's a good problem. Here's some intuition you should develop about Bayes' theorem. So first, Bayes' theorem, the whole thing is just multiplication and division. All we're doing here is estimating initial probability. Then we have our conditional probabilities, and we're just multiplying them out. We're just multiplying each to multiply and normalize, multiply and normalize. You may see some Bayes' theorem problems that have really complicated probability distributions. You might have use like a Poisson function or a normal function probability distribution. But that's only because they're trying to estimate some probability for a complicated problem. Maybe what's the chance of scoring a goal, or how long will we have to wait in line. So that kind of probability function is complicated, but Bayes' theorem itself is not complicated. The Bayes' theorem itself part is just multiplication and division. Next part of intuition, the whole reason we kind of skipped going over this problem is based around saying, what do I want to find one possibility, one of my possibilities? But in my opinion, it's just as easy to find all the possibilities as it is to find one possibility. The easiest way to solve these kind of Bayes' theorem problems is to make a table of all your possibilities and then solve for them. If you just focus on solving one column, then you really still have to do all the same amount of work, because you have to find your probability of every possibility in order to normalize. So it's really easier just to set up a table with all your possibilities, multiply them all down, and then normalize. Next thing you should realize is that the order of these results don't actually matter to the final result, so the order of these observations. So if we started with a negative test and then 2 positive tests, we'd still get 4% at the end for to have cancer. The reason is this is just all multiplication, and that's commutative, so you can change the order of it. And then finally, we've been normalizing every step. You don't actually have to do it. You could wait till the end to normalize, so I could just multiply these probabilities down and then normalize at the end. But when you do that, these probabilities can get very small very quickly, and at times some computer programs have trouble with numbers that small. If you're dealing with, say, 1e to the negative 50, then you start to get round off and truncation error. So I like to normalize each step. It just makes the problem easier, makes more sense. All right, so that's Bayes' theorem, an intuitive example. There's more to know. If you want to get this cheat sheet that I have, there's another example on here. This cheat sheet's available at fairlynerdy.com/Bayes theorem cheat sheets. And I've worked through half a dozen examples in Excel. You can download that Excel file with the 6 or 7 examples on fairlynerdy.com/Bayes theorem examples.